All right, so welcome back to System Software. Today we're deep in the middle of writing our compiler for our intermediate representation. We went over arithmetic last time, and just as a reminder, code gen 1 will be due today. That one hopefully will be pretty straightforward. You just spit out assembly code in a very formulaic boilerplate assembly code. And also today I'll be showing code gen 3, where you'll be extending your compiler to generate arithmetic and branching instructions. So we went over arithmetic last time, we'll go over branching today. Questions on generating arithmetic, questions on Intel's arithmetic instructions, how to use them, the AT&T syntax where the destination's on the right, questions about which operators to use, questions about division, questions about special registers. Okay, I hope it's straightforward. It's because we're doing an intermediate representation and not like C. You don't have expressions that you have to, figure out how to. It's largely a one-to-one or one to a constant number of instructions. So the languages are very similar. The tricky part is just going to be wrapping your head around this, the fact that you're generating code and not trying to evaluate code. Yeah.
I'm aware that CDQ extends by calling the size of a variable. But how does it do that and why does it do that?
You mean when you have Q at the end of?
No, CDQ to extend the bit size of a variable. Why is it wrong? Why do you want to extend it to one?
Oh, why do you have to run CDQ? Is that what you're saying?
To extend it, but why?
Why do you have to extend it? It's just the way the division operator is designed. It can basically take, I think, 128-bit divisor. I can't remember the words here. Dividend, sorry. Oh yeah, divisor. No, dividend. It can take a 128-bit dividend, that is the thing being divided, and then it takes up to a 64-bit divisor. So it's just the support you get for the division operation. I guess because it's division, they can support, if you just did 64-bit, then the result for many cases, I guess, would be a smaller number of bits. So for whatever reason, they designed the divider to be able to do 128 bits over 64 bits. The problem is that the registers are 64 bits wide. So if you want to specify a 128-bit register, well, you have to put the data into two separate registers. So the IDIV instruction assumes that you've populated the RAX and RDX register. RDX will be the high bits, RAX will be the low bits. It's assumed that you've already populated these registers with the dividend, with the thing being divided. And so in order to help you not have to fill out RDX yourself, if you just have a 64-bit dividend, this CDQ operation will sign extend. It'll extend the sign bit from the RAX register into the DX register. And that's just because, if you remember 2's complement or how negative numbers are represented. How are negative numbers represented in the machine or in many machines? Yeah. Yeah, 2's complement. And what ends up happening is that I always forget 2's complement. It always confuses me. I'm not a hardware guy. But the high bit will be 1 for negative numbers. So if you took RDX and you just set it to all zeros and you had a negative number, well, that 128-bit number is not going to represent the negative number you think. So if you just take that sign bit and copy it to all the bits of RDX, well, then you have apparently a 128-bit number that represents that. That's my understanding. So it describes it in here. Does this sign extension to the RDX. So basically, in our language, we're only going to have 64-bit numbers as the dividend and the divisor. We're going to put that number in RAX. But because the op takes RDX and RAX, we'll set RDX correctly by running CDQ first and then running the IDIV, the division instruction, to get the result. Does that make sense? Who asked it? You asked it, right? I don't remember who asked it. Other questions on arithmetic? So this is just specifics of the Intel 64-bit architecture. And this also kind of, yeah.
So the point of this division, like being so specific, is it because of the bits, or is it because of like the order of the operation? Like having like by specific, I mean like homologating it on one line.
What do you mean having, like, why do you need two instructions?
Or like why does the division instruction only take one?
Oh, it's just because the divisor, the thing doing the dividing, can be any register, but the dividend is just fixed to be RAX and RDX.
Okay.
So this is just the design of the machine. And so this kind of illustrates a point about why you would want to have an intermediate representation. It's a lot more straightforward if you're writing a compiler from C to, say, x86. It'd be a lot more straightforward if you could generate this simple IR. Generating something like this is a lot simpler to generate than having to know the specifics of the Intel instruction set, know which registers it has. And so the whole point of having this IR is to have a kind of simplified machine language. Also, other architectures may do things differently. They may not have a fixed register for it. They might not have division. Division, you might have to do it in software, for instance. So this kind of illustrates the benefit of having an intermediate representation in the compiler, is that it just eases the compilation steps. And at the extreme, there's even this actually new compiler framework called MLIR, which allows you to specify a whole hierarchy, a whole series of intermediate representations, each intermediate representation having some optimization purpose or having some purpose before you get to machine code. All right, any other questions on arithmetic? All right, so let's talk about branching. Branching is a little bit more complicated, but it's actually kind of similar to arithmetic. The way you handle operands, the way you do use the instructions. Okay, so the goal is to take our IR, which specifies gotos like this, where we have a label and a goto statement, which transfers flow of control to that label, and translate it to Intel assembly. So it looks very similar, right? Very similar for this kind of loop. What does this program compute? What does this program do? Can you guess? Yeah. What? Yeah. Infinite loop. Yeah, this is an infinite loop. But, it's a legal program in simple IR and assembly. So this is the main goal. We want to take branching operations that we have in simple IR and translate them to Intel's world, where they call them jumps instead of branches, but same idea. So any questions on the meaning of gotos in simple IR?
It's just basically a jump.
It's a jump. Yeah, it changes which instruction you're executing. So if you learned about the fetch execute cycle in CDA, did you learn about this? They call it the fetch execute cycle. So you have a stored program, and kind of by default, the machine will get the next instruction, execute it, and then increment the instruction pointer, increment the address that is holding the code, and then execute the next instruction. That will let you have a straight line sequence of arithmetic operations, but you couldn't implement more sophisticated computations like algorithms. So the goto instruction, all it really does is it just changes what the next instruction is that's going to run. So hopefully you learned about this in CDA. There is actually a special register called the instruction pointer in the Intel world, or the program counter, that holds the address of the next instruction to run. And what branching does is it really just rewrites that pointer to be a different address. For us in simple IR, you can think of each line as having a line number and go to changing which line you're going to execute in the IR. Questions about branching and gotos? Who's ever used a goto in C? Oh, interesting. Okay. You mean you implemented a virtual machine or something?
Just like on homework and stuff,
Huh, you had to write go-tos. So you ever heard that go-to considered evil? Ever heard this?
Like literally banned. They'll give you 0.
Oh, if you go-to. There are cases to use it. There are some special cases, but yeah. Okay. All right, so that's the goal. So the first thing to understand is what a label is. So labels are named locations in the program. So how is code stored in our von Neumann architecture machines? Where is the code stored?
Memory.
Right, in memory, in RAM. Where's data stored?
Registers.
Registers, where else are they stored?
Stack.
Where's the stack?
Memory.
In memory, yeah. So in the architectures we use, code and data are in RAM. Did you learn about this? Von Neumann versus Harvard architecture. We have separate code and separate data. So there's lots of ways to design where you put code. But in the architectures we're using here, RAM stores both code and data. So in some sense, code is also data, because code is a set of instructions. It doesn't live separately from the machine. It is physically represented in the machine. And how are locations represented in the machine level? Locations in memory, yeah. Yeah.
Coordinates on RAM.
Coordinates in RAM, yeah, it's just a number. It's just a sequence, like if you have byte addressing, which are the machines we're using do, you just have one number assigned for each byte in RAM. Yeah.
It's not well, what's the usage of byte alignment?
Byte alignment? You mean like 16-byte alignment?
Yeah, like you have a certain alignment. What's the point?
The point of so it depends on the machine architecture. So some operations will only work with specific alignments. Can't think off the top of my head. Like modern architecture is like byte aligned, so you have less restriction of that. It might be that, like for instance, the push instruction will have to be aligned to 8 bytes or 16 bytes. It may just be in the design of the architecture. I'm guessing it was easier to build the machine by assuming certain kinds of alignment. But again, I'm not a hardware designer, but that's my assumption as to why that's the case. So just as a quick refresher, we have RAM. At the top addresses, we have the stack. Near the bottom, we have the heap. But also somewhere in here in RAM, we have the code and other static data. And we start the memory addresses from 0. In modern systems, the lowest addresses are typically reserved for the kernel library. And addresses grow upwards to whatever the maximum size of RAM you have. Actually, it would be, because of virtual memory, you can have a fixed maximum size. But code and data, the point is that code and data and the stack and the heap are all stored in the same memory space. And in order to access a line of code, it's the same operation as accessing, say, data in the stack. It's just a memory address. So the way the whole fetch execute cycle works is it looks at a specific register to find the current address in code, gets that instruction, runs it through the processor to get the output, and then performs whatever state changes that the machine asks for, and then just increments the instruction pointer to the next line of code, and so on. So code is just data in memory, and locations in code are just memory addresses. Questions on this? Yeah.
Code instruction, if I remember correctly, is 4 bytes, right?
Is what?
4 bytes.
It depends on the architecture. I think Intel has variable length instructions. They're not always the same. They're not always the same length. So they're not. I don't think they're always 4 bytes. And that's you can save space in generated code. Yeah.
You could partition this to the address exchange. So if your operating system lives on one part of your storage only, and then something else lives on another one with the addresses for your system.
Well, so the disk, at least in our current architectures, this is my symbol for the disk. The disk is separate from RAM. It's a separate storage medium.
Yeah, but speaking
And-
of like the addresses in your
So the addresses in the storage world are done differently So it depends on the medium you have. So like I think disk storage devices, they have like sectors and bytes within those sectors. So certainly if you repartition, well, when you repartition, at least most tools I know of, will require you to reformat the disk and then copy data back. So if you do that, then there's no guarantee that you'll have the same position on the medium that you originally have. So the address on the medium, which is not the RAM address, will be different. But there are schemes in the file system level that make it so even the kernel is oblivious to where exactly on the medium on the disk data is stored.
So it depends on the scheme you use?
Yeah, for sure. So the scheme you use to actually store data on the disk will definitely affect where stuff gets stored. On disk, they use like effectively linked lists to help you find all the pieces of your file. And so those links are pointing to the physical addresses of the storage medium. So it is similar to RAM in the sense that you have a numbering scheme to specify each byte or sector or block on a storage medium. I don't know if that answers your question. But yeah, it's the same kind of scheme, but they have different design decisions for it. So this data is persistent, and you're probably not going to be accessing this. Like programs use variables and function calls to access different parts of RAM. But what do we use to access storage media?
Is it just the load instructions? Or those are for RAM?
Right, those are for RAM. So what do we use? So we learned about this a few weeks ago. How do we access, at least in Unix, System calls, the system calls handle that for us. So under the hood, there are I/O calls at the machine level that are asking for data from the storage medium. And this, again, depends on which architecture you have. Intel uses I think it's a port-based. They have instructions for interacting with other controllers that will ask, other chips that will ask for data from it. But you don't have the kind of direct access to RAM through a memory controller that you have with RAM. There are called memory map schemes where, I don't know how many architectures use it today, where they'll actually map part of the memory to disk or to other parts of I/O. And then you can actually do loads and stores to I/O. But in the kind of traditional architecture, storage media and other peripherals, they're considered like I/O. They're not considered part of the CPU memory hierarchy.
Unix handles it just like a file.
Yeah, so in the Unix world, all of the peripheral I/O is handled through files, a bit more or less. And then RAM is kind of its own. Now, there is actually a RAM file in Unix because anything can be a file, if you remember. So there is like /dev/mem, I think it's called. Yeah, so there is a file that actually is backed by RAM, and if you have root access, you can actually just start messing with RAM because you can treat anything as a file. But there's no, the I/O stuff is all kind of architecture dependent, and in the Intel world, you have to access a separate controller through a special set of like I/O instructions to access that. It's not done through RAM. But there are systems that do that. They have memory mapped I/O as well. But it's not going to RAM. It's just going to a special address. But anyway, yeah, interesting question. More for operating systems. Okay, any other questions on this code as data? Yeah. Yeah, well, I mean, the course, they're all good online textbooks. You can read the OS Dev wiki that I've given you. But yeah, it's more of in the realm of operating system design, how you manage this I/O. Okay, so labels are really just named locations in memory. But the question is, what does this label actually correspond to at runtime? So if I compile this program, the Intel architecture does not allow you to put a string for where you want to branch to. It's got to be a memory address. So what's the memory address going to be for this label?
Array X.
What's that?
Array X.
Array X?
Array X.
No, so RAX is gonna, the programmer has control over RAX. Yeah.
I might be really stupid, but would the label name be converted to a memory address and then be
Yeah, no, that's exactly right. No, that's not stupid at all. That's exactly right. So what the assembler does is it translates this name for you into a memory address. And the details of this are a little bit complicated, but basically, whenever you jump to an address, in the Intel world at least, jumps are relative. So this address will be an offset from the current instruction pointer. This is just how the Intel instruction set works. And let me show you the documentation of this. So without going into too much detail, but basically you have, let's see, where does it describe relative jumps? So it says jump near relative, displacement relative to the next instruction. So whatever let's say, let's go back to my infinite loop example. If this is address 3 and it says jump to loop, well, this is actually the same instruction. So it's just going to jump 0. It's just going to jump to itself. But if this were, 10 instructions earlier, it would say jump 10, negative 10. Yeah.
So does it call a function that creates its own stack frame, but jump and go to keeps it within the same stack frame?
Well, so these are, this is in the code segment. This isn't in the stack frame. So the stack frame is a separate part of memory from the code. So the code has its own memory address that it's stored at, and it's the instruction pointer that holds the current memory address. RBP is what's meant to hold the current stack frame pointer. So jump will just basically take whatever the value of RIP is, add the offset that you've given in the jump instruction, and then use that to update the RIP pointer. So a jump, more or less, is just RIP equal, jump X is RIP equals RIP plus X. This is basically what the jump instruction does. It's just a relative offset. Now, this X is not the label X. It could be any number as specified in this architecture definition, this relative address. But it's a number, and it's the assembler that will help compute this for you. The assembler will figure out what this relative offset should be looking at the label you gave it. Was there a question over here? Yeah.
Yeah, I was wondering what RIP was supposed to be again.
Which one?
RIP. RIP.
Oh, RIP is the instruction pointer. So IP, instruction pointer.
Is that already given, for every function call that you do?
It's managed by the processor. So when you tell the processor to run, it will automatically update the instruction pointer, pull the next instruction. This is the fetch execute loop that the processor has circuitry built in to do. It'll, when you do a call, remember what a call was. What does a call do? Remember the two steps that a call does in the Intel world? Yeah.
One is the return address, and the other one is it branches to the call function.
Yeah, and the way branching works, yeah, exactly. So it pushes the current return address, which is the instruction pointer plus 1, basically, plus 1 instruction. And then it branches. And what does branching do? Branching just overwrites RIP. That's all branching does. Branching is just let me set the instruction pointer to be a different address in memory. Questions on that? Does that make sense? So if I have a sequence, so this is my memory here, my code segment in memory. If I have a sequence of instructions, like move, compare, jump, etc., then the architecture has circuitry to get whatever the instruction at the current instruction pointer is, execute it, which means discover what its output state is, do whatever state updates it asks for, so change a register, load or store from memory, and then it increments the instruction pointer to go to the next instruction, and so on, and then just continues to update the instruction pointer to go to the next address. When it sees a jump, let's say this is jump loop, and in my assembly file I said loop was some instruction down here, then RIP, the jump instruction will change RIP to go to wherever the label we specified in the assembly file was. So this is why a function definition in the assembly world is just a label, basically. Because all a function call is at the assembly level is basically just branching, just changing the instruction pointer to another place in memory, to another part of your code in memory. Questions on this? I think this is in CDA, the fetch execute cycle, where you have a stored program machine and the machine has circuitry to automatically execute the instructions. The very old school machines, the operators would have to kind of enter instructions one at a time, kind of like a personal calculator. You enter the instructions yourself one at a time. But imagine you wrote down all the instructions you wanted to do first, and then just wrote a little algorithm that would read through each instruction one at a time. That's a stored program machine. And the next trick you can add to that is you can have a special instruction that changes which instruction to go to. It's kind of like, you ever read like a recipe or like a science experiment where it says like, step 1, get the beaker. Step 2, put water in. Step 3. And then step 4 is like, okay, go back to step 2. Right? You've all seen these instructions. That's all a branch is. It's saying go to a different step in my sequence of instructions. That's all branch is. And that's also why functions at the assembly level are really just branches. And all of the functional semantics are kind of emulated by us, the compiler writer, to make it look like we have like local state, recursion. Yeah?
Like these, I guess these calls like loops, just work similar to how the offset variables.
Exactly right. So to skip ahead for 1 second, what would, using branching instructions, what would it look like to implement an if statement like this, but in assembly or simple IR? Yeah. Some jumps. Let's try it. Let's try this as an exercise. What this? Let me get some scratch space here. So let's use. Should we use simple IR rather than let's use simple IR? So what would this program or this piece of the program look like? Well, actually, this is a tricky example. I just realized. Because I haven't introduced one type of branching. But let's take a guess. Yeah, what would something like this look like?
You need a label?
Okay, we need a label for sure. So let's put a new label here. Let's just call it like if statement label. So we're gonna have a label somewhere. So I haven't actually introduced like conditional branching yet. So maybe we can come to it. Yeah.
I might be a really bad guess, but basically, I don't know if you can do if statements in this, but if you can, I would say if x is greater than number 10, then I would go to the thingy.
Go to somewhere, right?
Yeah, and then in that somewhere, you're going to set x equal to 11, or move
Okay.
11 into the register for, or memory address for x, if that makes sense.
Yeah, so good reasoning. So we can, if we want to do, if we want to have programs that do something different depending on the input, we need to be able to test those inputs and change the behavior of the program. If we had no conditional branching, all programs, with a deterministic set of instructions, all programs that have the same output for the same input. Well, no, I shouldn't say that, because you can still have sequence of computations. But all programs would take the same sequence of steps in the program without conditional branching. So as your colleague astutely pointed out, that if we had a notion of conditional branching, we could implement this in our machine language. And so we indeed have conditional branching in the architecture level and also in our IR. We've got this new kind of goto, which first checks comparison between two operands. And only if that comparison holds do we do the branch. Otherwise, we don't branch. So implicitly, this instruction happens if x is less than or equal to 10. This instruction happens if x is greater than 10 because we jumped here. Because we jumped. Questions on this? Semantics? Yeah.
What if it was like a
So we weren't going to get into the to match that this class. You can take my compilers class for how to do that. But effectively, you're going to have to flatten or figure out how to do that with individual branches. So just like with functions, there's no notion of nested constructs in assembly. It's just sequence of instructions, and you can change what the next instruction is. That's it. So you would have to carefully design your jumps in order to emulate the same behavior of that nested if statement. So I think there was a question. Yeah.
Do you need another label to get back to increment it?
Well, so you mean this to this increment?
Yeah, would you need a label? Because then if it was over 10, would you just skip that part and jump to the other label? And then even after, if something label executes, we jump to the next label?
Okay, so you're already moving ahead to figure out how to do the rest of this. So how would you make sure that we executed x equals 11, but what about the program where x is less than 10? If we were to jump here, like let's say x is 9. So is x greater than 10? No, right? So then this would be the next instruction. But what's the next thing we run at this point in the program? Yeah, x equals 11. So this program, at least as currently written, even if x is less than 10, we'd still end up setting x equals 11. Yeah.
I was going to ask if we're doing that, why don't we switch the conditional so it's less than or equal to, and then move the x equals 11 up.
Okay, so that's an interesting idea, and it kind of reveals the challenge of trying to turn what you're comfortable, what you're used to in C into kind of straight line assembly code or sequential assembly code. All right, so let's see what happens when we invert that condition. So instead of x greater than 10, we observe that the next instruction the next instruction is what we want to execute if the statement is true, but we want to skip it if the statement is false. And so branches are better at skipping code because when the branch is true, we won't go to the next instruction. We're going to skip the next instruction. So let's call this false label because this is where we're going to jump to if this condition, or I should say this condition is false, then we're going to branch here. Actually, it's probably confusing to call it false label. Let's call it like else label is probably a more clear. All right, so with me so far on this, so x equals 9, we say if x is less than or equal to 10, then we branch to else label. Otherwise, if x is not less than or equal to 10, then we don't branch, which means we go here if x is greater than 10. We didn't branch. Questions on this? Does this make sense? Questions on this? Okay, so let's try to fill out the rest of this. And in the else label, of course, we want to do this increment, x equals x plus 1. Okay, so let's run this program for x. Yeah?
So where does the beginning of the program start? Or the beginning of the
The first line. The first line. Just like in a C program. Well, in the C program, the entry point is the main function. But in C and imperative languages, it's the first line.
Well, in this case, where does it start? Where should I look? Should I look at like the very first line of the text file? Or just
Oh, sorry. You mean like this?
Yeah.
Oh, it's my presentation. Sorry about that. Yeah. Let me get rid of the old one. Yeah, this is the code we're running. Yeah.
On the first example, can you
Yeah.
wouldn't you need to branch to a skip line to continue the code after?
You mean here?
About the STMC label.
To skip this one?
Won't you need to branch to a skip to do the x plus equals 1?
Well, we resolve that by inverting the condition.
Oh no, but I see if I use the above example. I would have to do that, right?
Yeah, you'd have to have another conditional branch to skip x equals 11. Is that what you're saying?
Yeah.
You'd need an additional branch, right?
Yeah.
So this way we avoid the additional branch. Yeah.
So it almost seems like it's easier to do the opposite operation.
It is, yeah. And actually, if you look at the compiler, like the output, it will invert the conditions so that, I mean, you don't have to. You could write the code in a way that did it, especially if you have an if then else statement. But it just makes the assembly code kind of look like the C code. So the idea is you skip when it's not true because you want to run this code. But anyway, this is just, this is a common trick in the compiler world. So all right, so let's execute this program. All right, so if x equals 9, in this program, what's supposed to happen? It's supposed to skip x equals 11, right? And then what's the result of x if x equals 9? 10, yeah. All right, but let's see if this code matches that. So x equals 9 here. Is x less than or equal to 10? Yeah, so we branch. Then our next instruction is here. And then we increment x, and it's 10. So it's all good, right? So let's see what happens when x is 12. So is x less than or equal to 10? So we don't branch, right? All right, let me say here first. So if x is 12, what should the value be for x equals 12? Yeah. What's that?
11, you said.
Yeah, it'll be, so x is greater than 12, it'll go to 11, and then the next line will increment it to 13. Right? So all right, so what happens in, yeah.
So why is it when we translate over the conditional, why do we always do the opposite instead of just checking it how it is?
Because of this. So if we check how it is, then we're skipping the next sequence of instructions. And then we'll have to do another test down here. I mean, we could do it, but you'd need a second check to make it work. All right, so let's see what happens when x equals 12. So we said here x should be 13, right?
No, it should be 12.
Oh, sorry, it should be 12. It should be 12. Oh, I'm confusing myself. X is greater than 10, it's 11, should be 12. So in this case, right, okay. So x is 12, it's not less than 10, so we don't skip it. It becomes 11, and then becomes 12. All good, right? All right, so let's take a look at a little bit more complicated case. And hopefully this will illustrate why inverting the condition makes sense. So let's add an else branch here. Let's see. Let's just do this. So if x is greater than 10, we set it to be 11. Otherwise, we set it to 20.
Is this just normal C?
This is C. C-like language. All right, so let's start with our condition again. If x is less than or equal to 10, we want to skip. We want to go to the else branch. And so what do we want to run if x is less than or equal to 10? What's the next instruction? Yeah.
Assign x.
What's that?
Assign x to 20.
Yeah, assign x to 20. So this is the inverse of our condition here. So in other words, we want to skip whatever the next lines are and go to the else branch. Yeah.
How come your assignment symbol in there is turning red?
I don't know. I think it's whatever the mode. Oh, it's in Lisp mode. That's why. So I'll turn that off so that it's. Okay, so the x label here, we set x to 20. All right, so what do we put if x is not less than or equal to 10? In other words, if x is greater than 11, assign it to 11, right? And then we're good. Yeah. Okay, so what happens if, I think I know what you're going to say. So what happens if x is 9? Then if x is 9, yeah, we go. This is true, so we branch, and now x is 20, right? Yeah.
Can you just say go to else label?
Oh, sorry. Yeah. This would be go to. That's the syntax of it. Okay, so questions on this? So if x is 9, then we skip all this, go to the else label, set it to 20. All right, but what if x is greater than 10? So let's say it's 12. Yeah.
It'll still be assigned, right, because that's the last instruction for it.
It'll still be assigned 20, so let's see why that is. So if x is less than or equal to 10, that's not true, right? X is 12. So this is the next line of instruction. It'll set x to 11. But what's the next line that we execute after this? Yeah, x equals 20. So this else statement is always being executed both times because we don't have structured code here. Yeah.
Why are you executing that?
Right, we shouldn't. It's not correct. So how can we correctly translate this if then else statement to, yeah. Yeah, we just use another branch to skip the else branch. What was the else branch in our C program? So I just want to illustrate the distinction between conditions in a structured programming language where you have this notion of blocks of code built into the language and how this differs from branching and conditional branching in the C level. So you're not going to have to worry about this too much in this class because we're not going to be generating IR. You're going to be computing stuff from the IR, but I will ask things about how to translate code like this into code like this. Yeah.
I mean, it's kind of like how switch statements work, right? I mean, you'll go through them one by one unless you tell it.
Oh, that's a good point. Yeah. So that's a good point. So in switch statements, you would have to say break, which really just translates to a go to the line outside. Actually, switch statements are often optimized as tables, but I guess they would still have they'd still need a break statement. But yeah, that's exactly right. It would still be, you have to tell it explicitly to jump out past the branch. Okay, questions on conditional branches in simple IR. So it takes two operands, a relational operator, and tests that. If it's true, then it does the branch if the test is true. And so just be aware when we actually, in like the compiler world, the meaning of this conditional branch is slightly different, or at least how the execution of it is slightly different because we have this assumption of structured code. How that gets implemented in real compilers is actually invert it so that you can put the if branch right after the conditional. Yeah.
What would you do if like you were doing an if statement instead of a loop and you wanted to do a continue line?
The continue would just translate to a go-to,
That's what, okay.
to the head of the loop, yeah. Do you want to see loops? Do you want to see how loops are done? Okay, let's see loops. So let's take let me make something fairly. See if I can make something pretty simple. All right, so here's my C-like language. I think this terminates. All right, so let's run through this program. What's the resulting value of sum for this program?
2.
I think it's 2, right? So step through it one line at a time, which is always good practice. X is 2, sum is 0. Is x greater than 0? Yes. So sum equals sum plus 1. Sum is now 1. X is x minus 1. So x is now 2. Is x greater than 0? Yeah. So sum equals sum plus 1. It's 2. Now x is 0. Go back to the while loop, evaluate it. It's not true anymore, so we exit the loop. All right, let's see how we can represent this. So I'll let you guys say, how can we write a simple IR program that has the same kind of branching behavior as this loop? Yeah.
You have to start with a label.
Got to start with a label. Okay. Let's call this label head.
And,
Why start with a label?
so like when you just jump back to the easy.
Okay.
Then we'll check the condition.
Okay. So let's this is reflecting the fact that in this loop you have to reevaluate the condition every time. So okay. So we have the We've got a label here. I'm going to call it head for head of the loop. Yeah.
Then
What's that?
add some one.
Okay, so let's add sum equals sum plus 1.
Don't you need like a condition before it?
Okay, so we're getting some pushback, and we need a condition. So what would the condition be?
I
Yeah.
think the condition is at the end. You should check if x equals to 0, you go to head.
Oh, so that's an interesting question. So you're saying the condition should be at the end,
Yeah.
or the condition at the beginning. There are several kinds of loops, and I see lots of hands going up. So yeah, go ahead.
I would do, honestly, what I would do is I would check if x is less than or equal to 0, do an else, go to the else label. In the else label, do nothing, I guess, or actually make an end label and it's sum. If x is not that, then we have to do sum is equal to sum plus 1, and if x equals x minus 1, go to head, do it over and over again until you go to the end of the x.
Okay, so let's do both of these options where we have the jump at the beginning or jump at the end. Let's do jump at the beginning. So what's the condition if we jump at the beginning? To exit the loop, right? Yeah. What?
If x is less than or equal to 0.
Okay, so if x is less than or equal to 0, go to end. We want to exit the loop or go to exit. So this is the same principle as with our if statement. You can think of a while loop as basically an if statement with a go-to in it, actually. And if this makes it easier to think about, you could rewrite this program as one way to think of this program is like this. These are basically equivalent programs. But okay, so let's continue this program. So we've got, let's move me down. So we've got the head of our loop. We've got the check if the loop condition is false, then we exit the loop. So this is how you check whether the loop condition is false. Otherwise, we enter the loop. And as your colleague already said, we need to go back to the top of the loop in order to continue to execute the loop, because that's the behavior of the loop, right? You continue running the body until the condition is no longer true. Okay, so let's execute this. Are there questions on this? Questions on this code? So it probably looks very, very much like this if we had translated our if statement. Oops. If we translated our if statement the same way, but put a go-to in our language, then it would look very much like this. This is very much like what the if statement looks like. Okay, so let's execute it. So x is 2, sum is 0. Is x less than or equal to 0? No. So sum is now 1, x is now 1. We branch back to the top of head. X is 1, so it's not less than or equal to 0. We go in to the next line, so it's 2. X is 0. Go back to the head. X is less than or equal to 0, so we branch to exit. Questions on that? So let's see what happens if instead we did the condition check on the bottom of the loop. So basically we run the body first, and then we check, is the condition still true? If the condition is still true, then we go back to the head. Or actually, no, wait, I can do the same thing. If the condition is false, we leave the loop. If not, we branch back to the top of the head. So all I did was move the condition from the top of the loop to the bottom of the loop. Yeah, you had a question? Oh, very good. Yeah, that's what I was getting at. This is the semantics of a do-while loop. Do you ever use a do-while loop in C?
Yeah.
A do-while loop actually looks very much like this. Do-while. The only difference between a do-while and a while is that the do-while always executes at least the body once. It's like 1 or more, whereas a loop is 0 or more. So yeah, that's exactly it. So your intuition is right. And actually there are I think some of these compilers will turn things into a do-while loop somehow. I'm trying to remember what GCC does, but yeah, that's the punchline, is that this is still a loop, but it's a do-while loop in terms of C. Yeah.
I think it's still the second one too, like, you made it too complex. I think if you just say if x is greater than 0, go to head, and then you don't need the next line.
Oh, I see what you're saying. Yeah, that's right. Yeah, you could rewrite this. So you're saying you could rewrite this with a single go-to. So you say x is greater than 0, go to head. Yeah, that's right. Yeah, you could write it like this. That's right. Yeah, you could write it like this. So it's just, yeah, you could write it like this. So if you don't want to invert the condition. But this is still a do-while, because this will always be run at least once. Questions on this? This is going a little more into compilers than I expected, but I'm glad there's some interest. Yeah.
Going back to what you said, the other guy, what would I like how you simplified it? Can you do that for like an actual while loop, not a do while loop instead?
I mean, put this on the bottom?
On top, how would you do that if you want to implement it?
That's a good question. Let's see. Can we design this where we check, I don't know, so we could have the body here somewhere. We say go to the body, otherwise go to the exit. Yeah, I think you could do it like this. Is this right? So you check the condition. If the condition is true, you branch to this body label, and that body label always branch back to the head. If the condition's ever false, then you don't branch to the body. Instead, you go to the next line, which is a go to exit. Does that seem to work? Yeah.
You can also have instead have two separate conditionals, one that's before the head and one that's after, like one at the end of the loop and then one before the loop even starts to check whether to enter the loop. So it'll like branch to exit.
So it's like this one, the original one we had before, but you also, oh, you mean, I guess you check up here to even not even enter the loop.
And we'll go to exit if, yeah.
So another variation. Like that, you were thinking? Yeah, that's another variation. So you don't have to worry about understanding each one of these, but you can notice that there are lots and lots of ways, technically infinite number of ways, to compile the same C-like program into machine code. And trying to prove the equivalence of programs in general is very, very hard to do. But hopefully this is at least some exercise to learn about this machine-like branching versus C. So in the same way that functions don't have a one-to-one construct in assembly, conditionals don't either. They have to be emulated with branch behavior. And you don't get this nice block structure that you have. You have to be careful with your remember that you're running each line at a time in sequence until you have a branch. All right, questions on conditional branching? This was a good deep dive into the semantics of conditional branching. All right, let's see what I was skipping here. Yeah, I think I covered all this. So yeah, that's same thing we went over. All right, so implementing this in assembly, just as a refresher, how do we access X's variable data when we translate this to assembly? Yeah.
You gotta know what its offset is.
Right, offset from the base pointer. So just to remind everyone. Okay, so let's see how we do conditional branches in assembly. So unlike our simple IR language where it's a single if condition go to, again, we've got two operations we have to execute in assembly and Intel assembly in order to perform this comparison. So the first is a comparison operator. The comparison operand will, as it says, compare the values of the two registers. I think it can also probably take an address. It'll compare these two registers. And just like with arithmetic, the registers are swapped. The left operand of the comparison is on the right. That's why RAX is on the right here. Yeah?
So where does it save the result?
That's a really good question. Where do the results go? So another idiosyncrasy of the Intel world is that there is a special flags register that gets set that is not explicitly readable by we, the users of the machine. Instead, what you do is you run this comparison operation, and then you pick one of a series of jump instructions, different jump instructions. So there is a different jump instruction for every comparison condition that you need. So you have jump less than or equal to, so let me actually show the whole table of these. You have a series of assembly jump instructions, Intel jump instructions, for each operator that we want. So we have jump if equal, jump if not equal, jump if less than or equal, jump if greater than or equal to. And so what happens at the machine level is this comparison instruction sets flags in a special flags register that is not directly observable by you. And then the jump instruction will read those flag registers and decide whether to jump or not based on the condition the condition that you've asked for, the condition code. All right, let me show. Okay, so what that means is that a statement like this in simple IR, where we ask, is x less than or equal to 10? If so, branch. We'd have to make sure that x, the left operand, is in RAX. The right operand's here. We'd have to run the comparison instruction and then branch if less than or equal to. Call the JLE less than or equal to op in order to do the branch. So our conditional branch in simple IR becomes two instructions, compare and jump, using the corresponding condition code that corresponds to our operator. Yeah?
I'll ask you a question. Can we put immediate values in the compare?
Yeah, you can. And you can actually, so you could put immediate values, yeah. You can even put memory values in there as well. So just like with all the load and store stuff, you can make a compiler to make fewer instructions, and you're free to generate the code however you like. I do things in ways that are like easiest for me to think about and easiest to write, and they end up being verbose because I know that there are compiler optimizations that will do that for me. Yeah.
So can we assume that that we're putting this label or not label? We're putting like the comparison in between RBX and RAX like we would normally. So this is comparing like if RBX is 10 and RAX is X. It's saying 10 is less than or equal to X.
Yeah, if you use the JLE branch, yeah. So there's lots of ways you could do this. You could swap these and then invert the condition. So what's the inverse of less than or equal to?
Greater than?
Greater than, yeah, not greater than, equal, greater than. So you could do RAX, RBX, and then do JG for greater than. And actually, to a little something that's interesting about the comparison operator is it's really just a subtraction op. It's a subtraction that does not save the result. So it turns out that all arithmetic operations, does it actually say it here? Yeah, the comparison is performed by subtracting the second operand for the first. Well, it's reversed in AT&T world. But actually these flag registers, which are described somewhere in here. I think I put a link to describe the comparison of the flag operators. But basically every operation you do, every arithmetic operation, the flag registers are always set. And the flag registers hold, is the result 0? Was there a carry flag? Is the result less than? And so every time you do an arithmetic operation, these flag registers are always set. And so you can think of comparison as turning the relational operator, which I think you probably know from like math class, into a comparison to 0. It's one way you can think of what the comparison operator does. Is it's you can always turn any. Well, it's sort of weird to see with this case, but if I have like x, is x greater than y, that's the same thing as asking, is x minus y greater than 0? And so at the machine level, this comparison is really just doing a subtraction and then checking the property of the result. Is it greater than 0? Is it equal to 0, basically? So that's why comparison is done this way, and that's why comparison is really just subtraction in the Intel world. But anyway, you don't have to like worry about those details. You can just remember that this is, if you want to generate a conditional branch in the assembly world, this is how you do it. You put the left operand here, the right operand here, and then call the corresponding jump instruction to implement this simple IR instruction. Questions on that? So this stuff is simple to the point of being difficult, because you have to be really meticulous about the operand order and the details of how to emulate a conditional statement in assembly, and the fact that comparison, there's no explicit saving of state. It's done for you by the machine. And that's also why jump LE just takes a label. It looks like an unconditional branch, but in the machine, it's actually checking these flag registers, checking these condition codes to decide whether it should branch or not. Okay, but I'm going to give, you have this, in CodeGen 3, you have like all the details about these instructions. And so it'll be pretty formulaic when you actually generate the code in the compiler. You don't have to be an expert in writing assembly. Yeah. I'm sorry, say again? Yes, CodeGen 3 is assigned today, starting today, and I have the project up. Questions on this? Questions on assembly? Yeah.
Make sure I'm understanding.
Yeah.
That's saying jump to false label if RAX is less than RBX?
Yeah, RAX is less than or equal to RBX. Yeah, this is saying, yeah. So this jump less than is saying RAX less than or equal to RBX. If that's true, then jump. So in the compiler world, I think what they'll actually, GCC will probably do is when we tried to compile a CIF statement, we inverted the condition. I think what GCC will do is it'll actually swap this jump here instead. It'll use the same operands, and then it'll convert. It'll actually swap this operand instead. We could test it, but we don't have much time left. But all right, so here's the whole table. This is the simple IR op. Yeah.
I take it Brent's gonna go over the project plus.
Yes, he will. Yeah, I think he did. I think he's doing the project. I gave it to him a little late, unfortunately. So hopefully he'll have finished the project by then, and he'll give you tips. Okay, so this is a kind of like template or pattern for how you do a. I forgot the actual label. So this is the kind of template for your compiler for branching. Oh, that's the wrong. Let me improve this a little bit. So this is the kind of template. Antler will give you the left and right operand. It'll give you the operator all as ASCII, and it'll give you a label. And you basically just plug those into a move to populate RA. Oh, this is one way to do it, but you populate it into a move. Just like with the arithmetic, you load or do the immediate load into RAX and RBX for the two operands. Then you always do the comparison. This is always what you do, at least in my scheme. And then you just pick the right opcode here in assembly and go to whatever the label was that was given to you. Does that kind of make sense? So this is where the pieces of simple IR go into. This is like a template for doing any conditional branch in Intel assembly, and then you just kind of fill in these placeholders. So that's how you do the branching part of our compiler. Questions on that? All right, so let me show a complete example. This is the one we had originally. So x is less than or equal to 10, go to false label. If it's not, go to the next instruction, which is x equals 11. And then what's the next instruction after that? It'll just be whatever the next line in simple IR is, just like in assembly. So let's see what the assembly code will look like. So here's the translation of our conditional branch. We got to get the operands. So why is this -8 RBP thing? What's that?
Offset.
Yeah, this is the offset. This is how we get X. And this is the immediate store of immediate copy of 10. Questions on this? Hopefully that's somewhat clear right now. Here's our comparison. It's always the same. If we design our compiler to do this, it's always the same. This is how I like to do compilers. I like to have compilers where I don't have to write a lot of conditional code. It's like everything's the same as much as possible. And then we have our branch. So in this case, it's based on whatever our operator is. We pick the corresponding assembly op and just copy whatever the false label is here. Questions on that? So there's an example of generating assembly code from this simple IR. Yeah?
Operands are the variables we're comparing.
Say again?
The operands, or we get operands, just getting the variables we're comparing.
Oh, sorry. I'm missing a space. This is just getting the source for RAX and RBX. So the X gets translated to here. This is how you translate X, and this is how you translate an immediate 10 in AT&T syntax. So this code, the code to do this is basically given to you in enter assign. I've given you enter assign, and the code in there actually shows you how to check the ANTLR operand and determine whether you need to do an offset or an immediate value. So that code is like, did I give it to you here as well? Yeah, I gave you this code. So this code will check for you whether the operand is a name or a number, and it'll actually give you the string of either the load or the immediate value. So you can check enter assign for how to do that. Okay, so that's the conditional. Here's, of course, the assignment. This is enter assign, at least my version of enter assign. We do the immediate copy to RAX of 11, and then same thing, this is the offset of X, so this is a store to update the value of X. Questions on this? Then we had our false label. How do we translate that to assembly? What does an assembly label look like?
Same thing.
It's the same thing. It's identical. It's identical in assembly. The syntax of labels is basically identical. And then we've got our X equals X plus 1, and this is more of the arithmetic part of, that's a little low. This is like the arithmetic part. That's what we covered last time. All right, questions on this? So hopefully this is mostly straightforward. If you got like code gen 1 and especially code gen 2, and you got the hang of emitting assembly code, which can be a little mind-boggling when you first do it. When normally we're writing programs to solve a specific algorithm to give us some like numeric or string result. In compilers, our outputs are other programs, and so it can be very tricky to wrap our head around this because we're writing in a programming language, and we're writing code in that programming language that's meant to be output and not evaluated. So if you can wrap your head around the notion of just printing out assembly code, and hopefully this will be not too bad, a little bit more straightforward. And so just review the lecture notes, review how arithmetic and conditional jumps work. I like to make things very, very template driven, where I don't have to do any creativity in generating the code. I just have a very simple template. And I've given, like for instance, this template that I gave you. So if you use a template like that, you can literally translate this to Python as printing this out, but replace these operands, et cetera, with Python variables that you set according to whatever the developer gave you in the input language. Okay, so for CodeGen 3, we'll be implementing arithmetic and branching. And so I've given you template code that has local vars and enter assign. And these are the only 4 functions you'll need to implement. Operation is the simple IR arithmetic operation that we talked about last time. Then we've got label, which is super, super simple. It's just spitting out the label and a colon. Goto, which is also very simple. It's just JMP and the label. And then if Goto, that's the trickier one, where you're going to have to test the operator, you'll have to convert the operands, and then generate that assembly template code. Let me show you one, and then I've given a description of what you need to output. So there's some helper stuff here like example code, how you can check the operator for conditional ifs in Python. This is how you can do it. And so here's where you would just set which assembly operand to use. Oh wait, that's not the operand. This is for arithmetic. Sorry, this is it looks very similar for branching. So this is how you check the operator in branching. It's the same idea. But let me show you one little facility I've given you. So one challenge is that go ahead.
Back up where you just were, what was the pass?
Oh, I actually that's funny you ask. I expected somebody might ask this. So it's just Python for no op. It's Python for don't do anything. And because of their indent specific world, you can't just like have an empty branch. So you use pass for an empty branch. That's all. It's a Python thing. All right. So so I've made it so that you can test this project even if you haven't done CodeGen 1 and 2. So these are all separate projects that you submit separately, but you can by all means copy your CodeGen 1 and CodeGen 2 code and see the joy of having a complete compiler. But you don't have to do that. You don't have to get CodeGen 1 and 2 right in order for this to work. So I've set up this little wrapper which gives you a pre-compiled assembly template that will automatically plug your compiler output into it. So let me show you what I mean here. This is the IR function that I've pre-compiled for you. So it defines a function. It gives you a bunch of local variables, hopefully enough for your testing. Gives you a result variable. And all the template does is it prints out whatever's in that result variable and then returns. So this you need CodeGen 1 and CodeGen 2 to do correctly. And so what you can do is you can modify this program to add the code you want to test. And so make sure you don't have any of the CodeGen 1 or 2 functions implemented. So just use the template that I gave you here. Yeah.
So we literally just copy everything from CodeGen 3 to that, or just something else?
You mean the template I gave you?
Like when we finish it, do we copy when it says add your code? Do we go all the
No, this is an IR. This is an input program. This isn't the CodeGen program. This is IR. So I've given you an IR template.
Oh, and I see.
Yeah, you can fit when you want to test it. When you want to test your compiler, you put in the code that your compiler will generate. So your compiler won't do anything for function, call, or return because you just leave those functions unimplemented, as it is in the template, as in the code template I've given you. And then you run this through your compiler, and it'll give you just a fragment of a complete assembly program. It'll give you just the compilation of this stuff here. And you run this make change directory wrapper. So I put a make file in here that will take the assembly template and glue it on either end of your compiler output so that you'll have a working complete program. So if you just follow these directions, you don't necessarily have to understand how it works, but if you follow these directions, just add your code here and then run make on it. It will put your code in the assembly file template and put the code that you produced in an assembly file template and then run it, and you'll be able to see the output. So put whatever you want to test in results, and it'll print it out for you. And this is how you can run. This is how you can run it. You can make several copies of these, or you can have several versions of it that you copy in or out of the wrapper. If you're interested in how it works, it just it has a template split into 2 files, the start and end of the template, and then it just runs your compiler on the input program and save it as a program called main.s.body, the instead of it. And then it just uses the cat command to print out the start of the template, your generated code, and the end of the template. And then that will give you a complete working assembly program that you can build and run if you want to do it yourself. All right, questions on that? So good luck on CodeGen 3. CodeGen 1 is due tonight, but remember you have a lenient late policy, and have a good weekend, everyone. See you next week. Sure, take care.